we'll be looking at the basics of exactly how total internal reflection works. In the second section, we'll be looking at how we can use it to do useful things. Now, we know from Snell's law that sine of r over sine of I equals n1 over n2. Remember that n1 and n2 are the refractive indices of the two materials that we're using. I is the angle of incidence of the incoming light, and r is the angle of refraction. So that's the refracted light. What if we had a ray of light moving from glass into air? So that means n1 is going to be 1.5, that's the refractive index of glass, and air is going to be refractive index 1.0. What happens if we set sine I very, very close to 1? Well, we can put it up in this equation here, can't we? Now, if we have n1 over n2, we have these values for n1 and n2, we end up with 1.5 over 1.0. Now, if we set sine I to an angle that we can choose, because we can choose the angle of the incoming light, we'll say that the angle of incidence is about 90 degrees, which means the denominator will be 1. So what will sine r be? Well, it'll need to be close to 1.5 if Snell's law is true. What angle can you take the sine of to get an answer of 1.5? Well, the problem is, sine is a very limited function. It has a range of only -1 to +1. So there's no way that we could get the sine of an angle equaling 1.5. We don't get any refraction. There's no possible angle of refraction. That means that we could get a refracted beam of light obeying Snell's law. So we get no light refracting at all. Instead, all of the energy that would have been refracted instead goes into the reflection. So all the light of the incident beam becomes a reflected beam. There is no light whatsoever refracted from the surface. This is called total internal reflection because we have no refraction. There's no angle which has a sine greater than 1. Now obviously, all the different transparent objects that we can have will have slightly different refractive indices. This means that for each one of them, there'll be a different angle where the total internal reflection starts happening. So we know that in our example before, we took an angle very, very close to 90 degrees. Even if we had taken the angle slightly less than 90 degrees, we still would have had total internal reflection, until of course we decreased it to a sufficient angle. Now that sufficient angle is what we call the critical angle. So if the angle of incidence is greater than this critical angle, we'll get total internal reflection. If the angle of incidence is less than this, refraction will occur normally. And that's mostly what we've been covering so far. Of course, if the angle is greater, then we get no refraction at all, and only reflection. Now it's possible to calculate exactly what the material's critical angle is going to be. And to do that, we can draw a diagram something like this. We have one material with a high index of refraction, like water or glass, at the bottom, and a different material with a low index of refraction, like air, at the top. All we have to do is set the angle of refraction to 90 degrees, because this is the maximum value that the angle of refraction can have. And of course, if we take the sine of 90 degrees, we'll end up with exactly 1. This means that if the incident angle gets any further away from the normal, the angle of refraction will need to have a sine greater than 1, which of course will lead to total internal reflection. So if we set the angle of refraction to exactly 90 degrees, we can apply Snell's law. In this case, the sine of the critical angle over the sine of 90 degrees will be the same as just the sine of the critical angle, because the sine of 90 degrees equals 1. And using Snell's law, we can get an expression for critical angle over sine of 90 degrees. That is, of course, n2 over n1. Total internal refraction only occurs if we go from a high refractive index into a low refractive index. So it can occur if we're going from water to air, but not if we're going from air to water. So when light passes the other way, that is, from air to water, then we can always find an angle for the angle of refraction as given by Snell's law, because the required ratio will never be greater than 1. Before, when we were talking about total internal refraction, we ended up needing a ratio of 1.5 over 1. If we were going the other way, we would have needed 1 over 1.5. and this gives us a number less than 1, which we can find an angle of refraction for. So if it is possible to find an angle of refraction, then light will refract. So when light passes through a prism, or a window, or anything else that it refracts through, then some of the energy of the light will be reflected. I'm sure that if you've ever tried to look out of a window at night, you'll see your reflection in the window. That means that not all of the light from inside your house is going through that window. Some it's being reflected instead, so we're losing energy. Of course, if we try to reflect light off a mirror, then some of the energy will refract and go through the mirror and be transmitted to the metal behind it. And so in that case, instead of losing energy to reflection, we're losing it to refraction. Light is being transmitted forward through the mirror instead of bouncing it back like we want it to. In total internal reflection, there is no refraction because there's no angle that we can possibly refract at. This means that we don't get any energy lost to refraction, and instead, the boundary between the two media behaves like a mirror. This is why if you're just underwater and you're looking up at the surface of the water at the right angle, it'll appear to be very reflective, like a mirror.